Okay, so let's begin our last talk today. Is by Vikas Jadhav from Wadia College, Pune. He's going to talk about G classes and rational conjugacy classes. Vikas, you can begin your talk.
Thank you, sir. I'll start my lecture. Okay, good evening, everyone. First of all, I would like to thank organizers and a special thank to Katre sir and Krishnendu sir for giving me a slot in this conference and arranging my talk at such a last moment. So I would like to start first of all with the little of my interaction with Kulkarni sir. I would like to tell. I started from 2004. I started at, after 2004. I started attending AFS, ATM school, AIS school, and during these AIS and AFS, I got in touch with Kulkarni sir, and I got highly impressed with by him. And then I thought I would like to work. I asked him that, can I work with him? So during AFS, he observed me and he said, yes, we can work together. And then I started working under him, and then he guided me. Every Friday we used to have seminars, and he used to take seminars every Friday, and that's the way we started discussing. And then later on, I started also work with Katre sir. And then under the guidance of Katre sir and Kulkarni sir, I successfully finished my PhD. I thank both of them from deep of my heart. And now I would like to start with my talk. Okay. Am I audible to everyone?
Yes, it's fine.
Yeah. So my title of talk is Z classes and rational conjugacy classes. So this is the outline. Initially, introduction, preliminaries, Z classes in P groups of order less equal P raised to 5. And then I will tell you a connection between Z classes and rational conjugacy classes. So we say that, as Anupam sir has already discussed, that two elements in a group G are in the same Z class if their centralizers are conjugate in G. That's a definition of Z class. And then we say that two elements X and Y in a group G are rational conjugate if the cyclic subgroup generated by X and Y are conjugate subgroups of G. That is the definition of rational conjugate. And in this talk, we will see a connection between rational conjugacy classes and Z classes. So these are the notations we'll be using. For a group G, ZG will denote the center of the group. ZGX denotes the centralizer of an element X in G. CG of X denotes the conjugacy class of X. And then Z suffix G of X will denote the centralizer. Okay. And for proper subgroup, we'll write H less G, and for subgroup, we'll write S less equal G. And N suffix G of H will denote normalizer of a subgroup H in G. So these are the notations we'll be using throughout this talk. Okay, so for computing the Z classes of P groups of order less equal P raised to 5, we have used some basic results in the P group from results from P groups. And these are the results which we have used. So if G is a P group acting on a finite set A, then the order of A is congruent to order of A sub G, where A sub G is a set of all fixed points of A under action of G. This is one result we have used. And then if a P group H acts on a set A such that P divides the order of A, and if A has a fixed point under G, then A has at least P fixed points. And then one of the very known result in P groups is that if H is a proper normal subgroup of a P group, then it's intersect center non-trivially. Then these are another results which we have used from group theory. If G is a finite P group and the index of center is at least PQ, then G has at most one abelian subgroup of index P. Okay, this is one of the important results which we have been using all the time. And for a group G, Z2G is subgroup of G such that Z2G mod ZG is the center of G mod ZG. So these are the notations, and these are the results related to that. So these results, all these results from group theory, we have used while giving the results regarding computations of Z classes of groups of order less equal p raised to 5. Okay, so these are also, again, these are the two lemmas we have also used, that G is a non-abelian P group of order P raised to N, and A is an abelian subgroup of index P. Then order of G is P times order of ZG multiplied by order of G dash, where G dash is the commutator subgroup of G. And if you have a group of order P raised to N greater or equal 4, then G has an abelian normal subgroup of order PQ. Okay, so these are all about little preliminaries about P groups. All these results regarding P groups we have used while computing Z classes. Now, this is again the introduction regarding the definition of Z class. So I will just try to reformulate it. So for a group G, we say that X and Y are in the same Z class if they're centralizer in conjugate. So if the group G acts on a set X, then you look at the Gx denotes the stabilizer subgroup of G at X. Okay, if their stabilized subgroups are conjugate, we say that two elements are in the same orbit class, and this equivalence relation, the classes under this equivalence relation, will be denoted by Rx. Okay, and when the set X is the G itself, then G acts on itself by conjugation, and the stabilizer groups are nothing but the centralizers. And in this case, the R of X is nothing but the Z class of X. Okay. Now we'll see the number of Z classes of non-abelian P groups of order less equal P raised to 5. So these are the results for now. After this, we have all results which I have done with Kulkarni sir and Rahul Kittore. These are all results we have developed regarding groups of order less equal P raised to 5. And this is being published in the Bulletin of Allable Mathematical Society. So one of the result is, let G be a non-abelian finite P group and H be a maximal subgroup. And if H is abelian, then H is a union of two Z classes. And then another result is, the lemma is, let G be a non-abelian finite P group. If the index of the center is P square, then G has P plus 2 Z classes. So these are the initial results we started with. Then if you look at the group of order P cube and P raised to 4 non-abelian P groups, P raised to 4 and P cube, then G has P plus 2 Z classes. And the proof of this is very simple. So if G is a non-abelian P group over at most order P raised to 4, then the index of the center is either P square or P cube. If the index is P square, then G mod ZG is isomorphic to CP cross CP. Hence, by above lemma, we can see that G has P plus 2 Z classes. And if the index of the center is P cube, then the order of G is of P raised to 4. And then G has unique abelian subgroup A of index P. And in this case, the Z classes are precisely G minus A, and A is union of two Z classes. So G minus A is union of PZ classes and A is union of two Z classes. So in all, we have P plus 2 Z classes. So we see that if you take any group of order P cube or P raised to 4, G has P plus 2 Z classes. So this proof was simple. I have, since the details of this, that G minus A is a union of PZ classes, I have not given. So this you can see in the paper which we have published. Then these are the results which we have obtained for the groups of order less equal P raised to 5. So if G is a non-abelian group of order P raised to 5 and the index of the center is P cube, then either the class of G is 2, that is G mod ZG is abelian, then G has P square plus 2 Z classes. And if the class of G, the class means I mean to say nilpotency class, is 3, that is G mod ZG is non-abelian, then again we have two cases here. If G has abelian subgroup of index P, then G has P plus 2 Z classes. And if G has no abelian subgroup of index P, then G has P plus 3 Z classes. So these are the results regarding when the index of ZG center is P cube. And then when the index of the center is P raised to 4, And if the class of G is 2, then G has P raised to 4 minus 1 upon P minus 1 plus 1 Z classes. And if the class of G is 3, then G has 3P plus 2 Z classes. Now again, here class 2 and 3. Now, so either class can be 2, 3, or 4. So if the class is 4, and then G has an abelian subgroup of index P, G has P plus 2 Z classes. And if G do not have, means if G has no abelian subgroup of index P, then G has P plus 4 Z classes. So we see that every time we make these cases, whether G has an abelian subgroup of index P or not. So that was a little important while developing the result.
Yeah, Vikas, please give some examples.
Yeah.
The theorem that you're stating with this index of the center,
Yeah.
you give some examples. Examples of those groups of order P to the 4th, which have said the center is of index P to the 4th.
Yeah, so examples are actually, all these examples I have stated at the end, sir.
Okay.
Okay. But these examples you can see. Or maybe I can list you from my thesis where I have listed these examples. I have not listed in this slides, but I will try to give these examples at the end.
Sure. Yeah. Good.
Now we will see the relation between Z classes and rational conjugacy classes. So we try to give an upper bound on the number of Z classes. And we also give a necessary condition for group attaining these upper bounds. And for the triangular groups, we upper triangular group, we find a necessary and sufficient condition. Means what is the achieve the upper bound. And for groups of order less equal P raised to 5, we see which groups attain this upper bound. That is what we'll discuss ahead. So for a group G, let CG be the set of conjugacy classes of cyclic subgroups of G, and Z suffix G be the set of all Z classes of G. And let phi from G to G bar, where G bar is G mod ZG, be the natural homomorphism. And for H subgroup of G, respectively H bar subgroup of G bar, let square bracket H denote the conjugacy class of subgroup H. Then we have this map H from C of G bar to ZG, that the equivalence class of the subgroup generated by X bar is mapped to R of X. So this map we have, and the proposition is this map is well defined and is surjective. And from the surjectivity of this map, we have this upper bound result. So what is that upper bound? If G is a group with index of center is finite, then the number of Z classes in G is at most the number of rational irreducible representations of G mod ZG. Now, you will see that the number of rational irreducible representations of G mod ZG or any group is equal to number of rational conjugacy classes. So that is the result you can see in Sayre's book. In Sayre book, it is given that you can refer that book, that number of rational irreducible representations of a group G is equal to the number of rational conjugacy classes. So here we see that the number of Z classes is always less equal the number of rational conjugacy classes of G mod ZG, not the group G, but the group G mod ZG. So that is an upper bound for number of Z classes. We can think of this in reverse order also, that number of Z classes is a lower bound for number of rational irreducible representations for G mod ZG. So both way we can think of this result. And this result follows from the surjectivity of H and the fact that number of conjugacy classes of cyclic subgroups of a group G is equal to number of rational irreducible representation. So this is the way we get this upper bound. Now we will see which groups attain this upper bound. So, and these are necessary condition. These are results related to this upper bound. If G is a finite P group and the center of G is P square of index P square, then the number of Z classes in G is equal to number of conjugacy classes of cyclic subgroups in G mod ZG. Means number of Z classes is same as number of rational classes, rational conjugacy classes of G mod ZG. Whenever the center is P square. And then another result which says that if G is a non-abelian group with index of center P raised to K, and if the number of Z classes is equal to the number of rational reducible representative of G mod Z, then either G mod ZG is CP cross CP, or G has no abelian subgroup of index P. So when the upper bound is achieved, then the structure of G is fixed, that G mod ZG is either a CP cross CP, or G has no abelian subgroup of index P. So using these results, we will see for special kind of groups, which groups attain these bounds. So let us talk about U and P for n greater equal to, let U and P the group of all n cross n upper triangular matrices with diagonal entries 1 over Fp. The group U to P is isomorphic to Zp, so it has only one Z class, and we can see the result holds. Then if you look at U3P, so U3P is a non-abelian group of order P cube. It has P plus 2 Z classes. We have already seen a group of order P cube has P plus 2 Z classes. And these are the representatives of these P plus 2 Z classes. And further, if you look at the quotient group is isomorphic to CP cross CP, and the images of these representatives in the quotient group generate P plus 2 distinct cyclic subgroups. Therefore, we can see that in this group also, the number of Z classes in U3P is equal to number of conjugacy classes of cyclic subgroups in the quotient group. So for U3P and U2P, the thing is simple. But for U4P, and so for U4P, we have to first of all get some structural information about U4P. The information is that this is a group of order P raised to 6, and a subgroup, this subgroup given here, is normal in G, and it is an extra special P groups of order P raised to 5. So this group mod the center of G is an elementary abelian subgroup of index P in G mod ZG. So this is one structural information we'll require to further proving that this group, in this group also number of Z classes is
Vikas,
equal
can
to the
you
number
just
of
tell what
conjugacy
extra
classes
special
of the quotient group.
Vikas?
Another structural information we'll require is for any X in G, the subgroup.
Vikas, can you hear me?
Yeah.
Can you just define what extra special P group means?
Extra special P group, I will just tell you.
You talked about it on the previous slide.
What happened? So actually, I'll just see the definition and let you know.
It's fine, we can check later.
Yeah,
Go
yeah.
ahead. Yeah.
Center is equal to the commutator. The quotient is elementary.
Yeah, center is equal to
Yeah,
commutator
in this group we
and,
have
G mod G prime.
and G mod G prime,
G
yeah.
mod ZG is non-trivial and it's elementary abelian. So extra special groups are like the center is quotient group is non-trivial and elementary abelian. That is what extra special P group is.
And center is also of order P.
Is it okay?
Center is of
Cent-
order P. I think.
And center is of order P. Center
Correct,
is of
yeah.
order P.
Yeah.
Yes, correct.
Okay, fine. Yeah.
So extra special P group is a group with is a P group with center of order P, and the quotient group G mod
Vikas,
center is a elementary abelian.
Vikas.
Yes.
Yeah, your slides are not proper, I think. I mean, something else that is showing.
Close the Chrome. Close the Chrome.
Close cross.
Okay.
Yeah, fine now.
Yeah. Okay. So is it clear now? Instantly, I could not answer. Right? It's okay. Is it clear now?
Yeah,
I'll
it's
repeat
fine.
again. So extra
No.
special P group is a group with the center is of order P, and the quotient group Z mod ZG is elementary abelian. Is it fine, sir?
Yeah,
Yes,
yeah,
yes.
good.
Okay, yeah. So that is what we have over here. That H mod ZG is elementary abelian subgroup of index P. Oh, so if you take any element X in G, the subgroup ZGX is maximal if and only if X lies in this quotient group. This is another structural information we'll require. And then if U and V are two elements in this quotient group Z2G mod ZG, then the subgroup generated by U and ZG and the subgroup generated by V and ZG, with this, they are not equal subgroup, then the centralizer of U in G is not same as centralizer of V in G. So from this structural information, we have these results, two results which we have developed, that if X and Y are Z equivalent in U4P, if and only if their images in central quotient generate conjugate cyclic subgroup, means in this group, the number of Z classes is same as number of rational conjugacy classes in the quotient group G mod ZG. And we have actually evaluated what are the number of conjugacy classes of cyclic subgroups in the quotient group is actually 2 times P square plus P plus 1. Is actually 2 times P square plus P plus 1. So in this group, number of rational irreducible permutations is 2 times P square plus P plus 1 for G mod ZG. So this is all about this triangular group. Now we'll talk about, okay, so I would also like to talk about the conjecture related to this. For a prime P and a natural number n greater or equal to, X and Y in U and P are Z equivalent if only if their images in the central quotient generate conjugate cyclic subgroup. Now for n bigger than 4, up to n is equal to 4, we have proved it. For n greater than 4, what would be the result? What is the result here? So for P, we are stating this conjecture. For general Q, this may not be, the conjecture is not true. If you take Q as P to the power K. So the example is, if you take U34, here the number of Z classes in G is not same as number of rational conjugacy classes in G mod ZG. So this example, so we have only stated the conjecture for U and P. So whether this conjecture holds for general P and n greater than 2, greater or equal to. For up to 4, we have verified it, but more than 4, whether it is true or not, we need to see it. So we have not checked it. Now then, if we have groups of order less equal P raised to 5 attains an upper bound if that is the number of Z classes is same as the number of rational conjugacy classes. If G is one of these type, either the index of ZG is P square, or the order of G is P raised to 5, index of ZG is P cube, class of G is 3, and G has no abelian subgroup of index P. Otherwise, either the order of G is P raised to 5, index of ZG is P raised to 4, and class of G is 2. And if, or the otherwise, the order of G is 2 raised to 5, index of center is 2 raised to 4, class of G is 3, and G mod ZG has this structure, C4 cross C2, semi-dot product C2. So this is very specific. So we have the structure of G mod ZG. The G mod ZG specifically should be like this, or order of G should be P raised to 5, and the index of G ZG center is P raised to 4, class is 3, and G mod ZG should have this structure CP square, semi-dot product CP square, where P is greater than 2. So for P greater than 2. And finally, either G should be of this type, that order of G is 3 raised to 5, index of the center is P raised to 4, class of G is 4, and G has no abelian subgroup of index P. So if G is one of these type, and G is of order less equal P raised to 5, then only it will attain an upper bound. So it's if and only if statement. So only these groups attain upper bound given here. The details of this are given below. So it will take time to discuss all these details because details are a lot of many. So this is what I want to say here, that up to P raised to 5, we have discussed which groups will attain this upper bound. Now another task is we can think of groups of order P raised to 6, which groups attain this upper bound. And even we can try to give necessary and sufficient condition for general P groups to attain this upper bound. So that we need to think about, which we have not proved yet. So that is what direction is remaining from our side. So I think that's what I want to say. And further, these are the details here. Details will take another half an hour, so I will avoid these details. So here are some examples, sir, that some groups are being explicitly given here. So these are some references. So I can say thank you. Happy birthday, sir, once again.
Thank
Wish
you.
you healthy
Thank you
life.
for your nice talk. Anybody
So-
has any quick question?
It's a very explicit work. I mean, you cannot
Yeah.
improve on this. Very explicit work. You cannot improve on this.
Yes, sir.
No, very nice explicit work.
Yes, sir.
You have published.
Published this work of up to groups of order P raised to 5, but this Z classes and rational conjugacy classes work not published yet, sir.
Is not yet published.
So I asked Katre sir whether we can publish it, but we are on to discussion with Katre sir. Maybe I'll discuss with the Katre sir, you or Krishnendu sir, Anupam sir. Think of publishing it soon.
Okay.
Maybe we can improvise on these results further, so we can actually give necessary and sufficient condition for groups attaining this upper bound. I think that will be more better result.
Yeah, hi, Vikas.
Yes.
I have a kind of question, like you're just looking for when this upper bound is attained. And here you see that G is some kind of central extension of G mod ZG.
Yeah.
So can you think of kind of building a tower, like G is sitting above G mod ZG, like this is what this co-class theory they build on.
Yes.
And then above G, there would be a E, so that G is isomorphic to E mod Z, E, and so on. And each stage, there would be some kind of equality.
Okay.
So either this is nearly impossible, or probably there is some extreme example where this kind of thing can happen.
Okay, I'll think about it, sir.
Yeah, this should not be like, there won't be too many examples. This is very much a very tight problem probably.
Okay.
Yeah. Thank you,
So
Vikas.
if anyone has any suggestion regarding this, Anupam sir, if you have any suggestion.
It's good work. We can discuss a little more, but yeah, really good. Thank you. And let's thank. Yeah, Professor Katre.
Yeah, how difficult do you think the higher case, P raised to 6?
P raised to 6, sir, it is possible, sir. But during my sir, actually, I left it during my PhD. I could not do it, but we can try it P raised to 6 also. No problem. But the classification of P raised to 6 we should know first.
That is known essentially. Yeah, that is known.
Yeah, that is known.
Up to P raised to 8, of course, it is more difficult when P raised to
Yes.
7, P raised to 8, and so on. But P raised to 6, probably one can manage.
Yes, that problem I can think of.
Okay.
Power 6 is, it's written down. It's around 78 or sometime.
Right.
Siddhartha is saying that it is P raised to 6 is written down. Yes.
So
P raised
can
to
use gap
8 is
also.
2000 pages proof. So it is not
I
published.
think this is what once I saw. I don't know.
No, sir.
Yeah.
In the survey article of Anupam Kumar, sir, he also mentioned that calculating number of Z classes in groups of order P raised to 6 is a problem. That we can think
Yeah,
of.
so one should try that now.
Yeah.
Okay,
that
thank you.
problem.
Nice talk. Yes.
Yeah. Thank you, sir.
Let's thank Vikas
Thank you, sir. Thank you.
more for his nice talk. Okay, thank you everyone. This is the end
Thank you,
of
sir.
the day today. See you all tomorrow.